Rabinovici, and okay, Eliezer, the podium is yours.
Okay, well, first, I think it's the first time I have the honor that my chairman is Shimon. I don't know Shimon a day over 45 years, I swear.
You will see muttering.
Okay. כן, אבל תעבור לאחד, לראשון. לא, זה הסוף. תעבור להתחלה. זה צריך להיות, כן. Okay, so I will start by reading some letters to David. These letters were sent by two letters that you mentioned yesterday. You were asked to compare your students, so you mentioned two letters. So these letters are from those two letters. Dear David, happy birthday. Thanks from all of us for all you do as a leader of our field, and all best wishes for many more productive and happy years. Edward. Dear David, I'm not sure why it's traditional to congratulate people annually for having become 1 year older. But in your case, there are more and better reasons to celebrate. Each year, your legacy in physics grows as your work continues to bear fruit, and your students and their students and their students' students, etc., etc. In short, your thriving physics family carries your flame forward. In celebrating your birthday, we get to celebrate our vital subject and our community, which you have so enriched as well. Of course, it's also a time to reminiscence. I had the pleasure of doing this with you directly a few years ago. I don't know how many. And now I'm going to embarrass you, and maybe myself, by going public a little. When I met you in Princeton, I was a graduate student in mathematics, ambitious but scientifically immature, in search of direction. You were more accomplished than I realized, and younger than I perceived. Nevertheless, I sensed, from very early on, your singular intellectual power and drive. And I was thrilled, not to mention astonished, that you were willing to engage me in long, wide-ranging conversations and reflections. Not always. And now, contrary to all what we heard yesterday, patience was not in those days your primary virtue. And there were big holes in my knowledge which sometimes got painfully exposed. But enough to encourage me and to make me want to work and think hard, so I'd have some progress to report or some new idea to share. For me, it was a transformative experience. Beyond facts and techniques, I picked up elements of your style, which did not come so naturally to me. The discipline, at crucial times, to focus sharply and to use equations and calculations as tools of discovery, which are especially useful to uncover exactly what it is you don't understand. As you know, within a few months, some very good things came out of those conversations. Looking back, I see them as a great gift and almost a miracle. Also fun. Thank you. Now, I see he added at the end, Dear David, congratulations on a life well lived. Best wishes for more to come, and above all, thanks. There is no signature, but this is Frank Wilczek. And Ofer will forward you the email, so I think you'll be able to read them. Okay, so as many of young in Israel know, everything is divided in 3 parts. So I finished now the first part. The second part is going to be an attempt to give, actually speaking to you, David, because I gave talk here to the Israeli community, and those who came will be a little bored. So I'll just take snippets of that. And then the last part, actually in your tradition, I'm going to ask questions. I'm going to ask each question first to you and then to the audience, and we are going to mark the results, and in 15 years we will have to check. I give a spot also in 5 years for a partial recheck. Okay, so the work I want to give snippets of our remarks on holographic complexity, geometry, and space-time singularities, work that I did with José Barbón. Some of this work was mentioned also by Gary, and I give you here a list of references on these papers. So I will try to address a few questions. One question I would like to address is, what does semi-classical geometry capture? So I'd like to give a statement on some cases and just say it's a little bit maybe in the line of things that Sasha was speaking about when he had this, in the trivial part of his talk, he had this appendix in the propagator, and maybe a little bit what Francois said. The diagnostic tools that one uses are very long-time correlation functions. But as you always like to hear about new things, I'm going also to introduce the notions which Daniel Harlow, who was in a winter school here a while ago, actually gave a very nice introduction to notions of quantum computing and trying to relate them to such type of questions. So the first question, not to keep you in tension, the answer is going to be that when you average, so you can call it inclusive, exclusive. So when you look at things inclusive, when you average, geometry can capture quite significant features. On the other hand, it cannot capture when you ask questions which are more detailed. And you will see what that means precisely. And this comes up in two cases, one in the black hole information paradox, and one in the issue which I think Eric mentioned, ER equal EPR. So the framework I'm using is ADS-CFT correspondence, but I will start first by introducing just the notion, something actually driven by Harlow, by Lenny, on the issue of complexity of, what is the complexity of a state, and then we will see how that comes back into the problems of gravity. So in order to define a complexity of a state, you need to be given a few things, and then hopefully the final outcomes, so there are universal features which don't depend on some of the ingredients in the definition. So you need to be given a simple, let's call it non-entangled state. You need to be given simple operations, which you can do. If it would be a Hamiltonian, let's say its parts are almost local. And then you define complexity by you counting the minimal number of operations that you are given, which should take you to any given final state from the initial state. And like this, you are able to assign a complexity to every state. So the simple example, classically, you have a system which is either 0 or 1. The operations you can do is move 0 to 1. You have S sites, and you can ask, if the operations are just moving from 0 to 1, you can realize in an order S, if you have S sites in the order of S, which is related to the entropy of the system, because the number of states is e to the S here, you are able to actually create all states. Now in quantum mechanics, the things go differently. And in particular, let's focus again on the issue of complexity. So that's in the column before the last. We are sitting here, so we saw that the complexity classically goes like order S. But quantum mechanically, it goes like e to the S. The reason it goes like e to the S is because you have to, in quantum mechanics, you have to have a superposition of the states, and this introduces the extra phases, which increase significantly, exponentially, the number of states in your system. Now, of course, by definition, and that's a problem, the thing is not well defined, because the minimal number of operations you need to do is a discrete number, while the phase space the Hilbert space you are trying to discover is continuous. So you need, from the beginning, actually, to introduce some type of resolution. But the nice thing is that by works of Kitaev and others, one has found out that there are universal features, even though you need to put in the resolution. The resolution, if it's epsilon, then you have a factorization of e to the S times log of 1 over epsilon. So the total complexity, the maximal complexity, goes like e to the S. And this you can just look at the number of cells which are available. There are order S choices at each step. So the total number of steps you can reach, states you can reach in n steps is S to some power, which means that the complexity, the maximal complexity, would be something like e to the S. Now, this was, again, you were given gates, you were given an initial state, and you were looking for the minimal number of operations that you need to do. When you use as the operator which does the evolution, the Hamiltonian, and not just some gates, then you can ask how does the time dependence of a complexity of a state look like. And then it will reach, and this, I think, nothing is actually really proven in this graph. But there are intuitive ideas on what one expects, how things are expected to go. This linear increase, for example, was not proven. There are strong indications from other cases that it could be true. But what is clear, we don't know if it's monotonic, but we can imagine that like entropy grows monotonic. Also, this thing more or less grows monotonically, and then you reach the maximum. And then, if you are in a system which is unitary, and if the system has a compact, or let's say discrete spectrum, then you are going to sit a lot of the time in that maximum, and eventually you are going to go down. And then this picture is going to repeat itself time and again. So this is just a statement unrelated to physics. It becomes related to physics if you decorate the different sections and you imagine that the creation of a black hole could be the first section. You could imagine some mixture, unclear what exactly the object is in the middle, and that's most of the time. And then the thing would come down again and go up again, and then it would be a white hole. Okay, now I would like you to note the similarity to something which was already looked at in the context and physical answers were extracted from, which is actually almost 1 over this thing. So consider now the thermal average of some 2-point correlation function. Look at it at very long time scales and ask how does this system behave. Now I'm going to give you some things which sound generic, even though at the end they're actually sometimes are true and sometimes the results are different, and I will indicate when that happens. So look at this long time correlation function. Just put e to the iht and e to the minus iht before the in the a of t, expand in a complete set of states, and if the spectrum is, let's say, chaotic or doesn't obey any conservation laws, then you just have a sum of many, many phases. And you can ask yourself what happens. Now, we know classically what happens. Quantum mechanically, there are cases where one also knows. There are semi-type of proofs. I don't think there are proofs for all cases, but there is a common wisdom. And the common wisdom is that the Poincaré recurrences indeed occur under the conditions I said. Namely, the system is unitary and the spectrum is discrete. And in order to realize what is the impact on this on quantitative measure of states, what you do is you take the average of this quantity and you try to ask what happens to it when you go to very long times. It's clear it's not going to vanish with an appropriate weighting, but it's enough to weight it with 1 over t, and in that case there is a lower bound to that system. This is just the name. You define the square root of that thing as the quantum noise, and there are various lower bounds you can find. One lower bound is an exponent. Actually, it's not minus s. You should put some number here, but it's of the order exponent of minus s. Another lower bound, which I will describe, would be 1 over square root of s. In any case, this quantity has an average, and therefore it means that if originally we looked at this thing, we thought maybe this would just thermalize and would just have an exponential or a power law decay if there are enough conservation laws. This thing can only go for a time, let's say, of order s if the bound is e to the minus s. Because after the initial exponential decay, this quantity will have to respect the average. So it cannot go below that. And then after a time which is called the Heisenberg time, you begin to feel that the spectrum is not continuous and the system, some phases actually already begin to move significantly. And then if you want to return again with some characteristic epsilon within the quantity, the value you started with, this will take a time of exponent of s. And will depend in detail on how particular you are when you want to reach. And let's say if you want Think of this as a sum of clocks. Each phase is a clock. If you want all clocks universally to reach where they were within delta phi, then you're going to get that this is going to be the time of recurrence of the system. Okay, so this is some fact that we had to learn in quantum field theory and we didn't learn maybe. I wonder, did any one of you learn this in his course in quantum field theory? No. Okay. But we should have known that. So I will skip this. I will just tell you, of course, to put everything in proportion, that these times are immense, the times involved. So UL, I will just tell you, just by the fact that the natural unit is universe lifetime, you realize that, that these things don't happen very frequently. On the other hand, if John Iliopoulos is here, then he is. Then, after all, John found about the charmed quark by looking at some process about who cared about flavor-changing neutral currents, which was a small, insignificant thing, which actually was a window to a lot of significant things. So I think when we have systems like ours, which are so robust and it's so difficult to find cracks in them, you look in the cracks wherever you find them, even if you have to be patient and wait 10 to the 87 universe lifetimes. So how does this now connect, this information on quantum field theory, how does it connect with the physics? It connects with the physics. Maldacena has said, let's use this quantity and let's calculate it in a context of ADS-CFT. And let's do the calculation at a finite temperature above the Hawking-Page transition. Let's look at it and see what it gives. So if you look at the effective potential which you need to solve of the type that, let's say, I could do in your background, you see that the potential when it goes to the horizon is continuous. So you violate the discrete spectrum hypothesis. And actually it turns out that not only you violate it, but you're also punished. And you don't get, in this case, the Poincaré recurrences. The spectrum just decays. So the average goes to 0. So how do you resolve that? That seems like a death blow to ADS-CFT. So the resolution is, from time to time, you know that this black hole also can become a thermal ADS. It's a configuration which is highly suppressed, but it's geometrical, and it can do that. You mentioned the word instanton, Sasha, let's call it instanton, even though I don't know if it's the correct okay, so some people do call this instanton. So in any case, this is another master field which is allowed. So you sit around it, and when you do around it, you see that the effective potential, instead of being like that, is actually in a box. You know that ADS acts as effectively as a box. So you regain the discrete spectrum, and you obey the bound. So ADS-CFT works. So that's great. The problem is that was for the average. But when you ask how does the object behave at any particular time, you know the answer from the CFT. And the answer is totally different than what you would get in the background of ADS. So the integrated information is correct obtained by ADS. But at each time t, you would get such behavior, while actually from the field theory, you see that you get such a behavior. And they give the same average, but they are totally different. So geometry, in this case, was able to capture e to the minus s effects, but also missed very important effects. Now, the type of, when I wrote e to the minus s, actually, one should specify that this is correct when you have chaos and you have the eigenstate thermalization hypothesis operators. Yes.
What is the dictionary that I missed in the ADS of this quantity?
You calculate the two-point correlation function. Again, the thermal average. So you the field. Yeah. So you take the fields. You take the fields on the boundary and you map them into the fields of the bulk. But given the restricted time of my chairman, park the question to the end. I will park the question to the end. Okay, then you go ahead and just qualify that when you have chaotic operators, when they are the ones which characterize the system, they give the exponent of minus s. If you have a system which is almost integrable, actually the noise is much larger, and what you would get as quantities like 1 over square root of s. So the e to the minus s is good when the typical, it's an interesting number when the typical dynamics is chaotic. If the typical dynamics is of conservation laws, then most operators, generic operators, will respect a much higher bound. Okay, so geometry reproduces average results. On the other hand, when it's not average, it misses also features. And it's interesting, and this is, one can show is general, that actually the configuration which is the least important will actually dominate when you ask about the average length. So it won't be the black hole which is a leading thermodynamical configuration, and you can do band structures and study that in detail and see how that works. Another place where the same observation comes is in the dual of is ER equally PR or not. As you remember, it was also mentioned here that Juan Maldacena and Lenny Susskind came with a counterattack to AMPS. They said, look, you all know we have an eternal black hole. In an eternal black hole, there are no firewalls, nothing happens. And then the counterattack was okay, but instead of having this thermophile double, very fine-tuned, highly entangled state, why don't you take a state where you put instead of a general, instead of n and m in the delta function here, put a general structure. And when they calculated the correlation functions there, they did not look at all like a geometry. And what you can do is, you can see that that is absolutely correct. But if you calculate, again, not the detailed time dependence, but you do the averages do not care if you what matrix G you have here. So it doesn't have to be a maximally entangled state. The noise itself, the average noise, will remain the same. So that would the second example where averages are given by semi-classical configurations. They are non-perturbatives, they're extremely small. E to the minus s is a very, very small number, and nevertheless it captures it. But there are other features which it misses. And these were these two statements, and I said it here. Now the next thing that we wanted to look at is following this work of Harlow, Susskind, and others, was to try and see how do singularities look in the presence in ADS CFT structure. And how much time do I have? So I will cut, because I need to take off for the questions. So tell me the cut. Okay. So there are a set of arguments, mostly dimensional, not proven, that the complexity when it changes in time should be linear, which means the derivative should be constant, and it goes like t times s. And then there was a claim which was related to things that Eric talked about and about how tensors reconstruct space, that it would make sense that the complexity be related to some volume, some extremal volume which appears in various circumstances. And the poster boy place where it appeared was actually as a Einstein-Rosen bridge and the length of the bridge. And then there are more general circumstances. So we go back to this problem. And the conjecture was that if you look at situations in black hole physics now, where the complexity increases, then no firewall will come up. On the other hand, if the complexity will decrease, a firewall will come up. But the claim was that it was highly non-robust. The first was very robust. That is, you could send the material which makes the black hole with another photon, and no firewall would come. But on the other hand, if you were in a situation where the complexity would decrease and you send an extra thermal photon, the horizon would be displaced enough so that no firewall would be formed. Okay, and they have made detailed calculations, and the object there, if you look here at the black hole, this would be the volume of the Einstein-Rosen bridge. You have, at each given time, on the boundary, you ask which surface crosses through these two times. You extremize it, and you plug it in. Now, that is a dictum. I mean, it hasn't been derived. And not only hasn't been derived, but the party line has been changed. And people have said that one should put in here maybe the action of what they call the Wheeler patch of this object. They promised that the calculations are much simpler like that. I'm afraid that they are not much simpler like that. And in any case, that part we did not succeed to do yet. We are doing the part with the maximal volume. So this were the results produced for black holes. Indeed, they were in the normal situation, the complexity all the time increased. Now, if you remember what I showed you before the graphs, the complexities cannot all the time increase. It should stop somewhere. And I showed you how the other object, the 2-point thermal average correlation function, how it is stopped from going to 0. Now, there we have a suggestive mechanism, and we know it must happen. Here we also know it must happen, but as of now, nobody has suggested what is the story which would actually stop the complexity from growing. So something must happen, and it should stop, but at this stage, it's not known what it is. So what we were interested in is actually we took the holographic complexity of various singularities. We assumed there is the volume prescription, so we look for the maximum volume, and we'll now engineer the singularities and check what happens to the complexity in each of the singularities. And again, I will give you, okay, so first I will tell you what was the method. So the idea was that, as we heard also in Gary's talk, the singularity reaches the boundary, the UV boundary, in a finite time. So actually one would expect that such systems can be described on the boundary by local boundary operators. If it would reach in an infinite amount of time, the operator structure should have been much more complicated. But if it reaches in finite time, it can just be with a set of either marginal or relevant operators, and you check what happens in each of these cases. So the result is that the complexity decreases towards the space-time singularities that we checked. And we were wondering a little bit if that is along what we heard in Mark's talk, the BKL phenomena, where as you approach the singularity, the problem actually totally decouples as if it was a strong coupling lattice. You just have each point acting on its own as a quantum mechanical system, and there definitely you're going to a state with low complexity. So the results are that in all the cases here, it happens. Now, why does it happen? So this is, I think, appropriate for what we are doing here, because you need theories with asymptotic freedom for that. And the reason why that happens is that the decrease in the extremal volume is actually dictated by the fact that the number of degrees of freedom is larger in the UV than in the IR. And this is what causes the fact that the complexity decreases. So this is actually, without showing the calculations, this is the result, and this is the source of the result. So now I can show one example of where this is done, and there was a question, but yes, David. Well, I have to show you the calculation. So I'll show you. Well, I don't know. There could be that it's related to what's happening on. You could maybe gain the intuition from the boundary, but the intuition we gained in this was from the bulk. So I'll show you I have to show you the particular calculation on how it happened on the house. So the cases we considered were a boundary conformal theory on, like what Gary described, on a Kasner case. That's the simplest case, because in that case what you do is you make the world volume decrease. So you just have the target space world volume decrease. So this is clearly a situation where you are going to have a singularity. And then you try and check what happens. You can do this is the Kasner, which was Gary took sum of pi in pi equals 0 in one of the cases, but the canonical thing, if you want a singularity, you need the conditions which were written here. And this is the object, and when you do the calculation, this turns out to be how the complexity behaves in time. So you see that it goes linearly with time, and the singularity, again, as Gary apologized, is a t equals 0 and not a t equal infinity. So when it goes towards the singularity, the complexity decreases, and you see that it actually counts the number of UV degrees of freedom. So that's the simplest case. Everything is in the UV. You made it, you build it, so everything is a UV, and the complexity decreases. Then you have situations where you can make the system with one dimension less, but let me skip that one and let me go to the case. Adam, are you here? With closed eyes. Excellent. No, don't open. Okay, don't open the eyes. Okay, so this is one of the situations which I find very interesting. And that is, there is a body of works which embody the fact that when you have some series, special type of series, which in the bulk seem to have a singularity, on the boundary, if you work with a certain slice, you have a singularity. If you work with another slicing, you don't have the singularity. And this is one of the things which amazes me, and I'm thinking of how to do that. And that is something you heard about before, David, but I want to share with you the thoughts on that. So the general framework is you take a look on the boundary, and like Igor a little bit described, you have either a relevant operator, or you break spontaneously the symmetry, or you have an unbounded operator. Each of these cases gives a different type of theory. Such a theory on a de Sitter slice gives a singularity. Such a theory gives a bubble of nothing. And such a theory is just unstable, both in the bulk and in the boundary. And the interesting things that I'm discussing are these. These are situations where the theory looks like just bread and butter spontaneous symmetry breaking in de Sitter space, while on the other hand, they reflect a singularity inside. So, okay, how do you see the singularity? Well, you do a conformal transformation on the boundary, and you go to an Einstein metric. Is Zohar here? Zohar is not here, so he asked about anomalies of the conformal what happens when you do the conformal transformations. Are there anomalies? This is not discussed here. This is a generic type of theory, and you see that both descriptions are the same. You can either have a catastrophe or not have a catastrophe. So this could be one point of view, like an ADS vacuum. Nothing happens to it. Don't matter in what, if it's an Einstein frame, in a de Sitter frame. His life would be very boring, but every configuration should ask itself to crunch or not to crunch. And how do you do that? So there are various criteria to check it. But to me, this problem looks a little bit like in T-duality. In T-duality, we are used to the fact that we all know, I hope you read, it was just one day after the gravitational waves were announced. There was another announcement which got less attention in the press, that one of the directions of the world was found to be a circle. And so we ask ourselves, why do we perceive that direction as large? We know string theory is correct, so how come we don't perceive it as small? So why did our brains evolve in such a way? And I think the answer is we live in local degrees of freedom, so momentum modes are the modes which we are ready, while global things like winding modes we are not built for that. And it could be the same thing as here. That is, somebody living in a universe which lives forever, like de Sitter, if he would build an observable which would be non-global and non-local and would be going fast enough, it would be able to declare that the end of the universe is coming. On the other hand, you could also find in a universe which shrinks, you can have an ostrich which is shrinking very fast, and he thinks he will live forever. So we need to find these non-local operators, and here I count on your help for that. If we go back to complexity, okay, you wanted one calculation. I'm happy with slogans, so for this thing. So here is the calculation. For example, you take a situation on de Sitter, you're searching for the maximal brane. This is the UV contribution, this is the IR contribution. You calculate them. Now, you mimic this by having a D brane which moves in space. So it has an ADS plus outside and the ADS minus inside. So it's clear that the number of degrees of freedom here is larger than the number of degrees of freedom there. And the contributions, one comes with a positive sign, the other comes, here it is, these are the calculations, the other comes with a negative sign, and this is just what you get. You get the number, the entropy, and this dictates that. So to conclude, complexity decreases towards a singularity. It's always taken with a grain of salt. Of course, you can't come too near when other effects don't come in. So you're just approaching it. The orders that you reach are much smaller than e to the s. It's the IR contribution, and this is for David, which increases. And the UV, you have a well-defined UV theory, and the UV wins. Okay, so what? So then the only answer to so what is maybe this resembles a little bit the simplicity in BKL. On this, I really don't know. The bottom line is I think it's a field in flux, and to my opinion, very interesting. Now comes, this is David, and I think at this stage, we see David is not totally certain. I mean, there is some, this is one of those rare moments where there is a processing going on. It's not yet clear how this will go, and I think that's the right moment to ask the questions. So let's do it. Now again, close your eyes. You're not interested in my desktop, even though this is the cleanest desktop I have. Do you see somewhere David lectures here? Yes, I see. Yes, I see. Okay. So here are the questions. So first, allow me, I mean, this is a case, a typical case which David actually chaired. And we are talking about the year 2000. There was a conference in Ann Arbor. I think the Indian conference had to be shifted a little to accommodate that conference. And there were the question of unsolved problems. So Ofer, please note now, because write so it remains. Okay, so the first question, and the best was of course chosen by David to be David's question. What else? And it is the following. So this is a top unsolved problem. You want me to read it, or can you can read it?
You have to read.
You have to read. I have to read. Are all measurable dimensionless parameters that characterize the physical universe calculable in principle, or some merely determined by historical or quantum mechanical accident and uncalculable? David Gross, that's his question. So first I ask David, what the answer to that? I give the 5-year span and the 15-year span.
The answer to that doesn't depend on the span.
It's known a priori, and it is?
I could give a probability distribution. Most likely, yes.
Okay. Okay. So, okay, the only way this can be measured, David, is you give odds. You give odds on a bet, and then it will become quantitative.
You're taking away about half of my.
So you want me to skip that question? You will answer it. You'll come. I'll park that question. Okay. But I want to take the opportunity. Who in the audience think that this will be in 15 years from now an interesting question? Will it be debated at all, or will it be something left to the history and sociology books? Who thinks this in a serious conference this will be a debatable question? Okay, never mind. It's not. You want? Okay.
He can record them.
No, he's recorded, but I'm not sure.
No, but he can say.
I can answer.
Okay, good.
I will say what the audience. Okay, so so I forgot what I asked. Yes or no? What sign? What sign was it? Will it be a debatable issue in 15 years, and will be part of a? Let's say I want to watch the faces. I want to remember. 15 years from now won't be easy. Okay, who thinks? Okay, no politics. Around the peak. Will it? I mean, nothing is said. In a peak of questions, will it be in the peak or not? Okay, so we got, I think, who thinks it won't? Who think it will not? Yeah, I mean, that's it. It will be over. Everybody would realize what the right answer is, and it won't be. It's not the same. Okay, it seems to me a majority that people think that in 15 years when Ofer will do this conference, he will ask that question again. Okay, so as I said, the time scales are 5 to 10 years. Okay, David, now this is not an EPS conference, it's not. We are here. Will one or more new particle be found in the next 5 to 15 years? Just yes or no will suffice.
Yes.
Yes, okay, yes. No, I take a vote. I mean, wishful thinking I do later. Now, David said yes. Now we can do our wishful thinking. Who thinks that in 5 to 15 years we will have a new particle discovered?
In an elementary particle.
Yes, of course. Sorry, where's Marek? Sorry, Marek. Yes, not. Sorry. Yes. No, that's not included. This was excluded now. Sorry. Who knows? Could be a very light particle. I don't. There could be very light. Let's not. We understand it's not something built out of quarks. Okay, in one way or another. So can you please raise the hands again? Wow, this is a believing field. Okay, and who thinks no? Okay, Ofer and Eva, maybe not surprisingly together. Okay, so you have to write a large majority says yes. So you know the field has wish. No, just in my mind, just in my mind. Okay, let's be more specific because you made commitments on that. Will some evidence for supersymmetry be found? Yes, you always answer first, so you can influence. No. Yes, okay, yes. I mean that Nati Zeiberg, in one of his papers, will write in the introduction, as is well known, evidence for supersymmetry has been found. Okay. Okay, that is noted. So I think the question, so who says yes? Okay, we have, here the number of believers has reduced. I mean, come on, how can the field survive with such little belief? Okay, who I have a feeling most will be neutral. Who says no? No, most says no. Okay, please be it recorded that most people don't think supersymmetry will be there. Okay, let's go to.
That's not the same statement. In 15 years, there will be no evidence.
Yeah,
It's
that's.
a different statement.
Then-
The supersymmetry will not be there.
No, I'm not. Come. We are not in a Talmudic. I think we know. The first approximation is what we take here, not the rest. Okay. Now, a particle physics evidence, not a change in the laws of gravity, but or in the concepts of gravity. I'm looking here on purpose to this direction, but I'm asking, will a particle physics evidence for dark matter be found?
Together with supersymmetry.
You can buy two at the price of one, Shimon. There is no problem. So who says yes? I beg you, I didn't hear. Well, afterwards you can add questions. Let me finish the ones I have.
Just dark matter, period.
Just dark matter and whoever it will be. I mean, a good candidate for dark matter. Forget any other name it may have. Who believes it will be found, the particle evidence? Okay. Who thinks that no way? Okay, the majority votes like that, and if it will turn out wrong, then it may be recorded. Okay, I don't know, for old time's sake, I took gut. That's just really for old time's sake.
How can you imagine that?
A proton can, I mean, there are many. Okay, I'm sorry, I go to the next thing. I saw this is not well defined enough, we don't have time to define better, I throw it out. Something unexpected happens. Just something that nobody who talked today could claim that he knew it. Okay, just experimentally, okay. Okay, no, unexpected, significant. Come on, again, we are doing what. This is not lawyers. I beg your pardon?
Doesn't matter what you found. Someone will claim they expected.
Yes, so I tried to remove it. Anybody in this room, I said, honest people. Okay, well, okay. TOE, let me throw out now. How about the decision will there be in the next 15 years a decision to build an FCC at CERN? There's another question. Don't worry. This is question number one. Will there be?
Depends on the answer to the next question.
Okay. So, will there be? Not now. What? Sorry. I beg. Will the future collider be? Will there be built in China in the next 5 to 15 years? Who believes? Okay, so now whoever believed that, I'm afraid it's mutually exclusive. So we go back. Who believes in that? Oh, okay. I said, well, it won't be built in 15 years. So you need a decision. Okay. Okay. Last question. Will quantum information be a useful ingredient in black hole and singularity physics, or will 15 years from now it turn out that was a flirt and the flirt was not, didn't teach us very much? It's not well defined enough, it wasn't clear enough. You don't want to take an opinion?
No. It's vague.
Okay. I bow. Thank you.
Okay. Okay, so now any questions to Eliezer?
I won't take questions now, I'm sorry. I
No?
refuse, so not now.
Okay.
The time, too much time.
Can you say your position on all these?
I can state them, yes, I can state it.
Okay. So we conclude this session and
Just before 1 minute.
wait, we have not yet finished. Wait. And before we ask David, he wants to say some closing remarks. We would like to say again, happy birthday to David, and to wish him from all of us many happy, productive years in good health. Now we've heard a lot of things, a lot of superlative about David during these 2 days, and I would sign each and every one of them. I could add more to my own experience, but I will not do it now. Instead, I will conclude, since we heard yesterday that David is fan of children's poem, we need a few lines from Dr. Seuss, and it's to you, David, and it goes as follows. You have brain in your head, you have feet in your shoes. You can steer your direction any way which you choose. You are on your own, and you know what you know. And you are the guy who will decide where to go. So relax and smile. Life is just to begin. You're in pretty good shape for the shape you are in.